Hey there, this is Lucius Laframboise from ENG Suite, and today we are going to learn about the two-way ANOVA. So, two-way ANOVA is a type of multi-factor ANOVA that's used to compare the effects and interactions of two factors on a single dependent variable. So if you remember from our previous videos, ANOVA stands for analysis of variance. And what we use it to do is to evaluate the effects of independent variables on dependent variables. And so two-way ANOVAs evaluate the factors individually to determine if the different levels of the factor have a significant effect on the dependent variable. So why would we use a two-way ANOVA? Well, a common example of a two-way ANOVA is the gauge R&R. Operators represent one factor and parts represent the other. The two-way ANOVA is used to determine if the different operators measure differently and if there's an interaction between the operators and parts. We'll get more into that when we get to the gauge R&R. But we can also use it during process characterization, especially when looking for interactions. So like let's say we have temperature and pressure and we want to see if there's a difference in, let's say cure time or something like that based on temperature and pressure. And we also want to know if there's an interaction, like maybe at a lower pressure but a higher temperature, we'll see a faster cure, something like that, that isn't there if or is more exaggerated when we have both of those factors. So when we're talking about an ANOVA, we're really talking about the ANOVA table, and we've gotten into this in the other two videos. But just to recap, the ANOVA table is divided into variation sources. Now for a two-way ANOVA, we'll see soon enough, we're looking into each individual factor as well as sometimes an interaction. And then we have the error and the total variation. Now, interesting, we'll get into this again, like I said, later with the gauge R&R. The error is called the repeatability measure in a gauge R&R. So each of these variation sources have an associated degrees of freedom, sum squares, mean squares, and then F and P values. And the F and P value are used to assess significance of the effect. So what sources are evaluated in our two-way ANOVA? Well, we have factor 1 and factor 2. So we evaluate the significance of the effects of different factor levels. This does not separate out our factor levels, and we can only use it to determine if there is a significant difference. So the significance of factor 1 and factor 2 only show whether or not different levels of that factor have an effect, not which levels have effects. Then error represents the variation due to the error between the regression model and the empirical results. As I mentioned before, GRRs, this is the repeatability source. And then total just represents the entire variation of the model, includes both factor and error variance, and gives you an idea of what kind of variance is going on in the system overall. Assessing significance. So this is like the major part of ANOVA. And in a two-way ANOVA, significance can be assessed for both the factors and the interaction using the p-value. Now, sometimes you'll use an F statistic or see it used and compared against a critical F, but p-values are more common because they are a comparison to the F critical, and they also represent your risk of type 1 error. And that's what your alpha critical value is. And generally, most organizations use 0.05, but check with your organization, make sure that you are using what your organization is supposed to be using. Just like with our one-way ANOVA, the null hypothesis here is that there is no difference between the treatments, the levels, and the alternative hypothesis is that one or more of these levels is significantly different. So null hypothesis, the factor, different levels of the factor have no effect. Alternative hypothesis, there is an effect with at least one. Okay, so how do we read the two-way ANOVA table? So here's an example, and this is actually the example that we're going to be using here shortly. So as you can see here, we look at our p-values, and we see factor 1 is greater than our critical of 0.05, so there is no significant effect at 0.05. Factor 2, 0.12, greater than 0.5, and interaction again. So what we see here is that there is no significant effect. But you see here our interaction has no significant effect. That means that we want to rerun the two-way ANOVA without the interaction term, because we want to see, okay, that's great, but without that interaction, this might be different, because the interaction actually affects your F and P. It doesn't affect your sum squares or your mean squares, but it does affect your F and your P values. So we rerun it. We rerun it here. And here we are with the same data, factor 1 and factor 2, just minus that interaction term. And now we see, without interaction effects, factor 1 and factor 2 are both below that 0.05 critical p-value. Therefore, we do see significant effects at different levels for both factors. So now we're ready to take a look at the math. And the math, we're going to do it first with interaction, and then, because as you saw with this data, there is no significant interaction, we're going to rerun it without the interaction. So first interaction, then without. Degrees of freedom, pretty easy. For the factor 1, it's just the number of factor levels minus 1 for factor 1. So the number of levels for factor 1 minus 1. Factor 2 is the number of factor levels for factor 2 minus 1. The interaction is your factor 1 degrees of freedom times your factor 2 degrees of freedom. Then error is going to be your total number of measurements minus the number of factor levels for 1 times number of factor levels for 2. And then total is just going to be your total count minus 1. So sum of squares, this is where it gets a little bit more complicated. So here the different factors are the same, just switching out the factor groupings. So the sum of squares for each factor is the number of factor levels for that factor times the total number of measurements over both factor levels multiplied together times the sum of the squared deviation of each group mean minus the grand mean. So each group mean is the mean of each level. And then SS interaction is going to be our total minus error minus factor 1 minus factor 2. So we're going to have to take a look down here at our SS error. And SS error is we're going to look at each individual group for each factor. So, you're going to say, okay, factor 1, group 1, factor 2, group 1, factor 1, group 1, factor 2, group 2, and then you're going to be comparing each of those individual values in those groups with their group mean. Again, this will make more sense when we get to Excel and we're actually looking at the workbook at all of this math. Okay, so then our sum of squares total, this is awesome. It's just the sum squared deviation of each individual measurement from the grand mean. Pretty easy to calculate. Mean squares, quite a bit easier. It's just the sum of the squares for each source of variation over its degrees of freedom. So SS of each factor over the DF of the factor, SS interaction over DF interaction, and so on. Now, in the F statistics, we only do it for factor 1, 2, and interaction. And so this is really where the difference comes from having an interaction term and not. So the F value for factor 1 is going to be the mean squares of factor 1 over the mean squares of the interaction. Factor 2 is going to be the mean squares of factor 2 over the mean squares of the interaction. And then the F statistic for the interaction is going to be the mean squares of the interaction over the mean squares of the error. Now moving on to the p-values, we in Excel can use f.dis.rt to get the right-tailed probability of the F distribution for the F value. So F of factor 1, and then our numerator degrees of freedom is our degrees of freedom for factor 1 because that was on the numerator. And then our degrees of freedom for our interaction is our denominator. And the same for factor 2. Except we use the F for factor 2, the DF for factor 2, and still the DF for the interaction. Interaction's a little bit different because now our numerator degrees of freedom for interaction is for the interaction, and then our denominator is the degrees of freedom for our error. Again, the F value is for the interaction term. But so here we have the summary of this table, all of the math here. And like I said, very shortly, we are going to go in Excel and actually calculate this. I just wanted to walk you through this so that you could see all of the equations for yourself. Okay, now we're looking at a no interaction table, and most of this is going to be very, very similar, with our degrees of freedom being the number of factor levels minus 1 for each factor, but our degrees of freedom for error is a little different. It's going to be our degrees of freedom total minus our df for factor 1 and our df for factor 2. And again, df total is the total number of measurements minus 1. Sum of squares is the same for our factors. The real difference here is going to be our sum of squares for errors, which is going to be our SS total minus SS factor 1 minus SS factor 2. Again, SS total is the sum of the squared deviation of each individual measurement from the grand mean. Mean squares, like I said, very similar to all of our other ANOVAs. It's just going to be the sum squares for each variation source over that variation source's degrees of freedom. F statistic this is where we start to deviate from the interaction. So if you remember from interaction, the F value there was ms of the factor over ms interaction. But here we don't have an interaction term, so our F for each factor is going to be the mean squares of that factor over the error. And that's why we want to rerun it, because now we have a different mean square for our error, so we have to rerun it to calculate a new and different F value. And then we can use that F statistic to calculate the p-value. Again, the same formula, f.dis.rt, and then our x value, our F value is going to be F of that factor. Our numerator degrees of freedom is going to be that factor's degrees of freedom, and then our denominator is going to be the degrees of freedom for our error term. And again, here is that table that summarizes it all super beautifully for you. That way you can see it. Go ahead and pause. This is a great reference for you. And now what we're going to do is head in to Excel and actually calculate this all by hand. All right, so here we are in Excel, and we have a lot of work to do. So first we're going to start with the two-way with interaction, and then, as we know, this is the data that we actually used in that PowerPoint, and then we're going to be able to get those results and then run without, because we do not have a significant interaction. Link in the description to download this workbook so you can follow along. The math will be filled in. Go ahead and delete that so it looks like what I've got here, and we will be ready to go. Okay, awesome. So here we have our factor 1 and factor 2 levels, a lot of different stuff going on. Let's start easy and get our grand mean. So here we're going to have our average, and over here you'll see our factor 1 has the levels here, and then factor 2 levels, and then our response. So each of these corresponds with this level factor 1 and this level factor 2. So we'll just take the average of all of our response, and there we go, we have our grand mean. Now to get our levels, what we're going to do here is we're going to say count, and then we're going to use the unique function, because it's going to pull the unique values out of our factor 1 array, and then it's going to count them. And we have two levels, 200 and 300. Perfect. Now we're again going to do count, unique, and then factor 2. Close it, enter. And then total. This is just going to be our total count. So I'm just going to do count and then count up our responses. And we have 8. Awesome. So here we are ready to take a look at our degrees of freedom. So degrees of freedom, if you remember, for each factor is going to be the number of levels for that factor minus 1. Again, we'll do number of levels minus 1. Okay, so I need to get my math up here because we have quite a bit to look at. All right, I've got it on on my other screen here. So now we're going to get the interaction, and our interaction is going to be our df factor 1 times df factor 2. Now our error is going to be our total count minus factor 1 level count times factor 2 level count, 4, and then our total is going to be our total count minus 1. Awesome. Now we're ready to start taking a look at the difficult stuff. And it really is difficult. It is the sum of squares. So what we're going to have to do here is get our different factor levels and our different factor level means. So what I'm going to do here is I'm going to say unique, and this will show you what the unique one does. And I'm going to select our factor 1 levels, and we have 200 and 300. And then I'm going to say unique here, and we get 80 and 120. Okay, so now I need to get the means of this group. And so what we're going to do here, first I'll show you, is we're going to use the filter array, and we're going to select our response array. So we're going to filter our responses based on whether or not our factor 1 equals factor 1 at 200. So now what I'm going to do is I'm going to absolute reference our responses. I'm going to absolute reference our response rows so that we aren't moving up and down as we drag this, and I'm going to leave that, enter, and you can see it returned 25, 22, 60, and 52. So 25 is 200, 22, 60, and 52. So now we have those values, and we're just going to say average, enter, accept, and there is our average for our 200 factor level 1. Drag this down, and now we have our average for factor 1 at 300. Now we can just copy this over here, and we're going to have to do a little bit of rearranging. So if you see, oops, it got bumped over a little too far, I'm going to turn that into column B for factor 2, and double click, and there we go. So again, same thing, we're filtering factor 2 based on whether, we're filtering the response based on whether factor 2 equals this factor level, and then we're taking the average. Okay, awesome. So now what we have to do for our sum of squares is equals number of factors, number of levels at this factor, times our n total over open parentheses, factor 1 level count times factor 2 level count, close that up twice, and now times the sum square, tab to open it up, sum square of our means minus our grand mean, and enter. And there we go, we have our sum squares. For factor 1, factor 2 is going to be the same thing, except factor 2 level count times n divided by open another parentheses, factor 1 times factor 2, close those both, times the sum square of our means minus our grand mean, and enter. Awesome. So now our SS interaction, we have to have our error in total. So we will just wait on that for now. So error, this is where we have to use these crazy matrices down here, this group mean matrix. Okay, so how I want to handle this is first let's work on our filter booleans, right? Because what we're going to end up doing here is, I'll start here with our group mean matrix. So we'll have temp and pressure. So these are going to be our temp values, so equals unique, and then we're going to select this, so we have both factor levels. And then for pressure, we're going to transpose this, and we're going to say unique, our factor 2 levels, enter. Okay, so what we want to do is we want to get the mean of the group where temperature is 200 and our our pressure is 80, our factor 2 is 80. So here, I'll say F1, F2, keep it simple. So F1 here, 280. Now we could just say equals average of this and this, but I'm trying to teach you how to use Excel a little more efficiently, and in this case it might not be more efficient, but this is all about learning math and learning Excel at the same time. So filter booleans. What I want to transpose unique. So these are our yes, and then I want to do the same thing, and then unique because I want to get our factor levels here. And what I'm going to do is I'm going to say, okay, equals this. I'm going to select that whole range, equals this factor level. So this is our factor 200 Boolean array. I'm going to do the same thing, except I'm going to do equals that and our new level. Again, same thing, except factor 2, this level, equals factor 2 equals this level. And now what we're going to want to do is we're going to want to do this. So concat, I'm going to say factor 1 level, absolute reference that, and then I'm going to do times, because this is our grouping, that, so it's our 200 by 80 group, our 200 by 120 group, and then we're going to equal concat again 300 and then 80, and I'm going to absolute reference that with an F4, and then awesome. So now what I want to do is I want to make sure if this and this are true, then that is part of the 200 x 80 group. Drag that down. Now we're going to do and again. We're going to say if 200 and 120, and we drag that down, and 380 and 300 and 120. Enter. All right, so now what we can do is we can use our filter again, but we're going to take our average of filter this array based on, so this is 280, that array. Close those up. There is our average of the group 280, and then I'm going to do the same thing. So average filter this array based on, and this is my 380 group, so 380. Yep, I'll accept, equals average, filter, select our responses, and I'm going to filter based on our 200, 120 group, equals average, and I'm going to say filter, response, and then our 300, 120 group. And there we go. We have all of our group means, but now we need our group deviations. So what I'm going to do here is just basically move these over. All right. So our group deviation, what we want to find out is the sum squared of each individual value in that group minus the mean of that group. So what we'll do here is we'll say sum squared of, and we're going to say filter our response by 280, because we're in the 280 group, minus our group mean. And then we close that up, enter, and there we go. So now we're going to do the same thing. So we're going to say sum squared of filter response, and this is our 380 group, and we are going to say minus that group mean. Yep, accept it. And then we're going to say sum squared of filter our response array by that 200, 120 group, and minus our mean for that group. And then we're going to do that again, sum squared of filter the response array based on 300 by 20 group minus the group mean. There we go. Now our sum squared for the error is just going to be the sum of these. There we go, 281.5. Perfect. Now our total, that's super easy. It's just the sum squared deviation of our responses minus the grand mean. Now we can take our interaction, which if you remember is our SS total minus our SS error minus factor 1 minus factor 2, 120.125. Awesome. Now we're on to the easier stuff, right? So I'm just going to adjust this over here so I'm looking at it. All right. Mean squared is just the sum square divided by the degrees of freedom for each term. And I want to go all the way down. Now, if you remember, our F statistics is just going to be MS of our factor over interaction, MS of factor over interaction, and then for interaction, it's MS interaction over error, and then our p-value is f.dist.rt, f df factor df interaction equals f.dist.rt, f df factor df interaction, and then f.dist.rt, f interaction, df interaction, error df. And there we go. We have our two-way ANOVA table, but let's check it out, see how much easier it is in QE Suite. So we'll do ANOVA two-way. Come over here, select our factor with our factor name, factor with our factor name, response with response name. And for this, I'm going to say, yes, we have an interaction. And there we go. Everything looks exactly the same. So like I said here, we don't have any significant interaction, but we don't have significant effective factors, but we don't have a significant interaction. So we're going to have to rerun this without the interaction. So here we are in the without page, and this one's a little bit easier. So to start, we're going to start from the same spot. We'll do equals QE, equals average of our responses. So now we have our grand mean. And again, we want to get our count unique from our factor level 1. Yep. And then count unique of factor 2. And now we have our factor level counts, and we want our overall count, total measurement counts. Awesome. So now we are ready to take a look at our degrees of freedom. So degrees of freedom for factor 1 is just the levels, minus 1. Factor 2 is the level count, minus 1. Our errors, let me scroll down here so I can get the chart up. And then error is going to be our df total minus df1. So let's just do it. So df total minus df factor 1 minus df factor 2. And we get -2, but we don't have our total. And that's just our total measurement count minus 1. And there we go, looking great. Time for our sum of squares. So again, this is where it gets a little bit complicated. For this, we want to, again, get our factor level means. So I'm going to take my unique values out of factor 1, and then my unique values out of factor 2. So these are unique levels, factor levels. And what I'm going to want to do is, again, take the average of the filtered array of our responses based on whether or not factor 1 equals our factor level. Yep, except the typo. And again, I'm going to take the average of the filtered array of responses based on whether or not our factor 1 level, equals 300, and close those up. Now our means for the factor 2 levels is going to be exactly the same. Average of the filtered response array, so filter our response based on whether or not factor 2 equals this level, and then close that up. Again, we're going to take the average of the filtered array of our responses, whether or not factor 2 equals 120, and close that up. Awesome. So now we're ready to calculate our sum squares of factor 1, and that equals the number of levels for that factor times n total over factor 1 level count times factor 2 level count, close those up, times the sum square of our group means minus our grand mean. Enter. There we go. Again, factor 2 is going to be the same. Level count for factor 2 times open parentheses total n over open parentheses factor 1 level count times factor 2 level count. Close both of those up times the sum square of our means minus our grand mean. Great. Now for the error, that again is going to be similar to the degrees of freedom, but with SS total minus SSF1 minus SSF2. And we need to calculate our total, but that is surprisingly easy. It's just the sum squared of that entire array minus the grand mean. And there we go. We have our sum squares. Now we are ready to get a little bit easier here because, as you're used to, our mean squares is just our sum squares of each divided by the degrees of freedom for each. Now, as I mentioned, for the F value, this is where we deviate from the with interaction to the without interaction. And this is why we have to run it again, because we calculated a new mean square for the error, and we're actually using the error instead of the interaction. So we take our MS factor 1 over MS error. And then we're going to do the same here over MS error. And now our p-value is f.dis.rt with our degrees of freedom numerator factor 1 and error equals f.dis.rt of f factor 2 and error. And there we go. You see these are very different p-values. Now we do see that there is a significant effect of factor 1 and of factor 2, but there's no significant interaction of the two. So let's run this with QE Suite just to see how easy that is and why you don't want to be doing this all by yourself. And we'll do factor, response, and declare false interaction. And there we go. We didn't have to program anything. All right, so that is ANOVAs in Excel, two-way ANOVA in Excel. I hope this was helpful for you. If you're doing a lot of ANOVAs, this method only works with this specific number of factors and response variables. So go ahead and get started with your free trial of QE Suite. It's awesome. It's 2 months. You'll be able to run ANOVAs like no problem. If you have any questions about any of this math or on how to get started or how to just do better in Excel, go ahead and reach out to me. I'm happy to help. Email in the description. Thank you so much for watching. Have a great day. Please do something.